A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians, welcome back to another video. And today it's getting serious. Like literally, we are going to evaluate a series, and I hope you are going to enjoy this video, which has been sponsored by the wonderful people over on Brilliant. More information at the end of the video. Please watch the entirety of the video. It seriously supports the channel. And now we are going to dive right in. Now this series right here is going to yield a pretty boring result. I mean, it depends on your views on mathematics, if it's boring or not, but the journey to get there is quite fun, at least in my opinion. And it took me a tiny little bit to figure this one out because my usual approaches didn't work. So the first thing I checked with the series is if it converges. Now, it does. If you do the ratio test, you are going to notice that it's going to go to 0. So overall, this thing is going to converge in the process. It also converges absolutely, by the way, but this really doesn't bring us closer to the actual answer to the problem. And here's where my regular methods didn't work out. In the only case, what I try to do is, if I have a fraction like this, do stuff like partial fraction decomposition to break this multiplication of denominators up into the addition of two fractions. Didn't work out. So I was a tiny little bit stuck, but then it struck me. Now this right here is an infinite series, meaning n ranges from 0 to infinity. What you can do to evaluate series is you can actually get yourself the value of the finite summation of those sequence members and then take the limit as n or k approaches infinity, so our upper bound, to get yourself the value of the series. So what we're going to do is we're going to reformulate this into the limit as k approaches infinity of the finite sum where n ranges from 0 to k. And this is just a reevaluation of this problem. It's just the same stuff, but we are using calculus here a tiny little bit. So this is 1 divided by n factorial times n plus 2. Now what we are going to do is we are trying to get ourselves the partial sum formula. This is what this is going to evaluate to. And if we take the limit of the partial sum formula, we are going to get our limiting value, which is the solution to our problem. Now, I also got stuck here a tiny little bit, but this actually brought me closer. And what are you going to do if you can't deal with a series or maybe a finite summation? Well, you just write out members and see where this is going to get you. And at first, we're going to take a look at k being equal to 1 and see if we can spot for k being equal to 2, 3, and so on, a certain pattern. So for k being equal to 1, what are we going to get? Well, let us plug everything in. This means that the sum runs from 0 to 1. We have 2 members in total. The first is 1 over 0 factorial, which is 1 times n plus 2, so 0 plus 2. Overall, this is just 1/2 plus. And now the second member. When we plug 1 into here, this is 1 over 1 factorial. So this right here evaluates to 1, and then 1 plus 2 is 3, so 1/3. Okay. So 1/2 plus 1/3 overall is nothing other than we can find the common denominator, which is going to be 6. And up here we get 3 plus 2, which is 5. Okay, fair enough. This is right here, kind of like the second member. Okay, this is the first member if we let it run to 0, and the second member if we let it run to 1. Now what about k being equal to 2? Obviously, we preserve our original members, so 1/2 plus 1/3 is overall nothing other than 5 over 6. And we get the next member where we plug 2 into here. 1 over 2 factorial, this right here is going to be 2. And then times 2 plus 2, this is 4. So 2 times 4 is 8, so we are going to get plus 1/8. Now, if we were to add those together, once again, we get a common denominator of, I mean, you could multiply it together. This would be 48. Or you could find the least common multiple, which would be 24. And now, if we bring this up, we get just 3 if we expand this 3, and here 4. So this is going to be 20 plus 3 is going to be 23. And now we can already spot a certain pattern, and maybe it holds up for the next one, and maybe the one after that. Our numerator is going to be 1 less than our denominator, which is kind of cool. But for now, I couldn't really see any connection between our k and maybe, for example, the denominator. This is something I wasn't able to see. So what I did, I took the next member and see if I could spot the pattern in some kind of way. Now, we are going to get the members up until 2, so 23 over 24, and then plus the next one. If we plug 3 into here, this is 1 over 3 factorial. This is 6. 3 plus 2 is 5, so we get 1 over 30. Or this is the same as 1 over 6 times 5. Why am I rewriting it as 6 times 5? Because, just like before, we could just multiply those together by 4s and see which fraction we are going to go. We are going to get, or we are going to go smart at it, and we are going to search for the least common multiple of the denominators. And you're going to notice that we nearly have 24 down here. How are we going to get it? By expanding by 4 over 4. So we get 24 times 5. So the only thing missing is 5 divided by 5 here, expanding. So what we are going to do is we are going to expand this by 4 over 4, and this right here by 5 over 5. And this is going to result in a common denominator of 5 times 24 is the same as 120. And this is where it really struck me. And retrospectively speaking, it was actually kind of obvious before. But here it was really the point where I said, well, I can spot the pattern now. 120. And we could take a wild guess here and say that our numerator is going to be 119 because it seems to be always one less than the denominator. Is this the case? Where we get 4 here and 5 times 23 is 100 plus 15 is 115 plus 4, 119. And I think this settles it for us. So what we are going to get is, and this is an ugly curly bracket, I am apologizing to all you curly bracket fetishists out there. This is an abomination. Now, we try to find a connection between the fraction that we have here and also our sequence members. And it really becomes obvious because if you take a look, 6 is nothing other than, this is 3 factorial. And over here in the numerator, we get 5, which is 6 minus 1, which is 3 factorial minus 1. Okay, cool. Now, obviously, we get 24, which is 6 times 4. This is 4 factorial by definition. We get 4 factorial minus 1. And now 120 is 5 times 4 factorial, which is 5 factorial. So we get 5 factorial minus 1 divided by 5 factorial. And I think you can see the pattern here. Now we just need to connect k to, for example, 3. So k being equal to 1, and we get 3 here, where 3 is 1 plus 2, and then factorial. Now does this hold up? K being equal to 2? Obviously, 4 is 2 plus 2, factorial. For k being equal to 3, we get 5 factorial, 3 plus 2 factorial. So it's kind of obvious if you take a look at all those members here. We are going to get overall that for the kth member, it holds. So for k element of the natural number, it holds that we have our partial sum from n being equal to 0 to k of 1 divided by n factorial times n plus 2 is the same as k plus 2 factorial minus 1 divided by k plus 2 factorial. And now we found an actually really nice form because this right here is the addition or subtraction of a numerator, meaning we can break up the fraction into k plus 2 factorial divided by k plus 2 factorial. No matter how you look at it, it's 1. And then we get negative 1 over k plus 2 factorial. Now, guys, it's Chase Station. If we now take the limit on the left-hand side, we're going to get our series out that we had initially. But we can also take the limit of the right-hand side and see what we are going to get. Now, what is going to happen if we take the limit as k approaches infinity of 1 minus 1 over k plus 2 factorial? Now, obviously, 1 is not affected by it. It's a constant. So we only take the limit as k approaches infinity of negative 1 over k plus 2 factorial. Now, this is going to give us 1 over infinity factorial. You can get a value, which is finite for infinity factorial. I made a video on that, maybe linked down in the description. But in fact, obviously, factorial grows rapidly to infinity for x equal to infinity or k equal to infinity, meaning 1 over infinity is going to strive to 0 overall. So the value of our infinite series is gonna be 1. And as mentioned before, that's kind of the boring result, but for some people it's actually quite beautiful because 1 is the multiplicative identity. It's a beautiful number. It has been a prime number for ages, and I hope you did enjoy what you have seen today. And if you want to see more mathematics, then why not try out the contents of today's sponsor, Brian, who are kind enough to sponsor yet another video here on this channel. Mathematics is a traditionally notoriously hard subject, but it doesn't need to be like that, because in today's day and age, there are various sources, from books to online courses, which can help you get better at math in no time at all. And one of those amazing sources is Brilliant, which provides you with some of the best online learning content that you can find out there on the internet. With their nearly 70 interactive courses in all topics STEM, they provide you with knowledge and a density of facts that you could never find during your time at school or maybe at university, because they do something special. They not only give you formulas and the abstract stuff like I did here. No, what they do is they give you graphics, many graphics and interactive things to play with to find out more about, for example, infinite series. You can not only calculate this stuff, no, you can also graph the members of this finite sum, just like we did here, and plot it. And then you're going to see that the limiting value of this infinite series on a graph is going to be equal to 1. And they do this a lot. Their entire course concept is based on visualizations and trying to make it easier for you to understand very complex topics in a very interactive and also visual manner. It's highly intuitive what they offer to you, and I invite you to try it out today for completely free by using my link at the top of the description, brain.org/flammymaps. You can try it out. 30-day free trial of amazing awesomeness. Everything. Take a look at it. See if it's something for you. And if you feel like this could turn into a long-term relationship between you and their content, you can also use it on the go, by the way. They have an app. Then you can make use of the link entirely and get 20% off an annual premium subscription, which is an amazing deal considering how much content they already have available on their website and how much content they are adding on a regular basis. They are adding new stuff all the time, and Christmas is around the corner. So you should check it out. They love to post some new stuff over there for the Christmas season and also for New Year's. And it could also turn into a great Christmas present for your loved ones if you have someone who's also doing something in the STEM field. So you should definitely consider getting yourself a premium subscription and see if it's something for you. And this would also highly support the channel. So check it out and support the channel this way. I thank you guys for watching. Hope you did enjoy what you have seen today, and up until the next video, I wish you guys a flammable day. See ya!